Welcome to section 4.2. Today we're going to talk about the two most important subspaces associated with a matrix A, and those would be the null space and the column space. I've started us out with a proof that H equal to the set of all x in Rn such that Ax equals 0 is indeed a subspace of Rn. Now, you can all read, so I'm not going to read through the proof, but I do want to point out the three requirements to show something is a subspace. So if you have a subset of a vector space and you want to show it's a subspace, you have to show that the 0 vector is in that set. You have to show that set is closed under addition. So if you take two vectors in the set, show that their sum is in the set. And finally, you have to show the set is closed under scalar multiplication. So I did that, and you can read through that. Now let's talk about a null space, because that subspace is indeed called the null space. So this is the definition. The null space of an m by n matrix is the set of solutions to Ax equals 0. So this is null A, and you should know this definition. Now let's just talk a minute about the dimensions. We have an m by n matrix A, so A is mapping Rn to Rm. Remember, the dimensions flip, and so the x that we're referring to lives over here in Rn, and it's getting mapped to 0 in Rm. I'm not sure if I've used this notation before, but when you're showing a certain element goes to another certain element, use arrow with straight bar on the left. Okay, and the theorem is the null space of a matrix is a subspace, and that's the proof at the top of the page. In linear transformation language, we call the null space the kernel. So it's the kernel of a linear transformation. So let's do some examples. Show that H equal to this set of vectors is a subspace by showing H is the null space of a matrix. Okay, well, the only thing that would work here is R4, because H is a set of vectors in R4, A, B, C, D. Let's rewrite these two equations that were given. 2A plus 3B minus C equals 0. So I'm going to write this as a homogeneous linear system. And then negative A plus B plus C minus D equals 0. So in matrix form, that linear system, the coefficient matrix is 2, 3, negative 1, 0, and then negative 1, 1, 1, negative 1. And then we have the vector A, B, C, D, and that equals the vector 0, 0. So the zeros are in R2, and the vectors are in R4. And the matrix we seek, A, is the coefficient matrix, 2, 3, negative 1, 0, negative 1, 1, 1, negative 1. And H is equal to null A. Because again, let me reiterate, the null space of a matrix is a set of vectors that get crushed, they get sent to 0. All right, let's get two more. Now H is the set of vectors in R3 such that this equation's true. And we want to know if that's a subspace of R3. So this is an easy one. We'll just go with the low-hanging fruit. It's easy if you know how to do it. No, since the 0 vector is not in H. 0, 0, 0 is not contained, that's a containment sign with a slash through it, in H. Because when we put 0, 0, 0 in for ABC, 0 is not equal to 4. And that's the first requirement to be a subspace. You have to have the 0 vector. Okay, next one, we're going to get a lot out of this, but I've done all the computations for us. We're given a matrix A, and we want to write null A as the span of a set of vectors. So what I did was I reduced A augmented with 0, because null A is the set of solutions to this equation, Ax equals 0. So to solve that, we augment A with 0 and reduce. Okay, and so we're over here with this matrix, and we see that there are two non-free variables. X1 and X3 have pivots, so those are non-free, and the other variables are free. So I'm going to start at the bottom. We haven't done this in a while. X4 is free, so I'll call that T. X3 is not free, it's 6T. X2 is free, let's call that S, and X1 is negative 2S minus 13T. So let's write the solutions in parametric vector form. X bar is equal to our S vector. The coefficients of S are negative 2, 1, 0, 0. And the coefficients of T are negative 13, 0, 0, 1. So if I call this vector v and I call this vector w, the solutions are linear combinations of v and w because s and t are parameters. They can be anything. And so null A is equal to the span of v and w. And that's exactly what we were trying to show. So we're done. Two things I want to point out. And in the next section, these will be important when we find bases. The spanning set, v and w, those are automatically linearly independent. Whenever you solve a homogeneous linear system, the vectors that span the solution set will be linearly independent. And the second thing I want to point out, so that was the first thing. The second thing is the number of vectors in the spanning set will be the number of free variables in AX equals 0, because each free variable gives you a letter like S or T, and that will correspond to a coefficient vector. Okay, column space. This is a little more straightforward. If you have an m by n matrix, the column space is the space spanned by the columns. How do the dimensions work? Well, let's just look at an example. If you have a 2 by 3 matrix, 1, 2, 3, 4, 5, 6, 2 by 3, the columns live in R2. So that's the part about the column space of an m by n matrix is a subspace of Rm. All right, and so the theorem, the column space is a subspace of Rm. The subspace part we learned last time. The span of a set of vectors is automatically a subspace. And in linear transformation language, the column space is simply the range of the linear transformation. Okay, so now we can rephrase some old results with our new vocabulary. The first old result is that AX equals B has a solution if and only if B is a linear combination of the columns of A. Well, if B is a linear combination of the columns of A, that means B lives in col A, because column A is the set of all linear combinations of the columns of A. That's a mouthful. And the second result, AX equals B is consistent for all B if and only if the columns of A span Rm. Well, another shorter way to say that is col A is all of Rm, because again, the span of the columns is col A. So let's just take a look at the comparison between null A and col A. If A is an m by n matrix, A maps Rn to Rm. Null A lives over here. Null A is a subspace of Rn. Col A lives over here. It's a subspace of Rm. And AX equals B is consistent for all B if col A is actually equal to Rm. So it takes up the whole space. So let's look at it in a couple of examples. The second example is, I think, the most valuable one. But this first one, show H is a subspace of, the only thing that could work here is R3, because H is a set of vectors in R3. And I just want to point out that I wrote here X and Y are in R, but I could have just left that out and it would have been implicit. I could just say H is the set of vectors that look like this, and it would be implied that X and Y are real numbers. Okay, we want to show that H is col A for some A. So let's rewrite this vector X minus 2Y, 3Y, X plus Y as the sum of an X vector and a Y vector. So if I write X here, the coefficients of X are 1, 0, and 1. And then Y, the coefficients of Y are negative 2, 3, and 1. So in matrix form, that's the matrix 1, 0, 1, negative 2, 3, 1, X, Y. So if I let the matrix A be 1, 0, 1, negative 2, 3, 1, then H is equal to col A, and that does it. Col A is the set of linear combinations of the columns of A, and that's exactly what this is. So we actually answered this question appropriately for how it was phrased, but you could also say that H is a subspace of R3 because H is equal to the span of a set of vectors, and those two vectors, if I call this V and this is W, H is the span of V and W. That also makes H a subspace because spans are automatically subspaces, but it doesn't answer the question the way it was phrased. Okay, let's do a comparison between null A and col A. So I've got a 2 by 2 matrix and a vector. Is W in null A? All right, so that's asking, i.e., is AW equal to 0? Does W get crushed? Question mark. All right, so that's an easy computation. We just compute AW. 1, 2, negative 1, 1, 1, 2, and we get 5, 1. That's not equal to the 0 vector, 0, 0. So no, W is not in null A. Is W in col A? All right. Well, now we're asking, i.e., is AX equal W consistent? So let me just scroll up to the top of the page. Col A is the set of all B such that AX equals B for some X in Rn. So in this case, our B is actually W, but we want to know if AX equal W is consistent. So again, that's going to be a computation, but now the computation is we're going to reduce the augmented matrix A augmented with W. So that's 1, 2, negative 1, 1, dot, 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 1, 2, and we reduce. I'm going to replace row 2 with the sum of row 1 and row 2. All right, so right now I see I have 2 pivots, and so I know that AX equals W is consistent. So I know my answer is yes. However, I want to go a little bit further. If so, write W as a linear combination of the columns of A. To do that, we need to find a solution. Those will be the solution will be the coefficients of the columns. So let's keep going. I'm going to scale row 2 by 1/3. And now moving down here, I'm going to replace row 1 with negative 2 row 2 plus row 1. 1, 0, negative 1, 0, 1, 1. Okay, so my coefficients are negative 1 and 1. That tells us that W is negative 1 times column 1 plus 1 times column 2. Or, write that a little more cleaner, negative C1 plus C2. So it's worth taking a moment to study this example and look at the difference between being in null A and col A and what that means, especially in terms of computation. Okay, we're almost done. You should pause the video and see if you can do the problems on this page yourself. Okay, hopefully you did that. Is H a vector space? Well, we've got 2 options at this point. We could show that H is null A for some A, or H is col A for some A. Now, since we're given an equation set equal to 0, I'm going to go with the first option, H is null A. So let's rewrite this equation in matrix form. Think of this as a linear system with just one equation. 1, negative 1, xy equals 0, and that's a 1 by 1. So our A is equal to the coefficient matrix 1, negative 1, and H is null A. So yes, the answer is yes. Okay, now we've got a 3 by 2 matrix. So A maps R2 to R3. Col A lives over in the target space, so that's a subspace of R3. And null A is in the domain, that's in R2. Find a non-zero vector in col A. We'll pick one. Col A is the set of linear combinations of the columns of A, so certainly any column of A would be in there. You could use that one, or 2, 0, 0. It's almost too easy. Find a non-zero vector in null A. Well, now we want a solution, so we want any solution of AX equals 0. So we reduce the augmented matrix A augmented with the 0 vector. All right, that's already reduced. X2 is free, that's T, and X1 is negative 2T. So our solutions look like X bar equal T times negative 2, 1. Now I want any non-zero vector in null A, so I could take T equal to 1, and I get X equal negative 2, 1. Okay, and that is the end of this section.